A changing magnetic flux induces a current and an EMF. So last chapter we talked about how how a current can generate a magnetic field, but now we're going to talk about how a changing magnetic flux can induce a current and a voltage. And here we have a couple of examples of how this can happen. So in this picture here, we've got a magnet, a bar magnet, north poles facing up. We have a coil of wire here, and we move the magnet up through the coil, and that induces a current within this loop. Okay. And we pull the magnet back out of the coil, and that reverses momentarily the flow of the current direction. And we can see that here with the different directions in the current depending on whether or not I was increasing the magnetic field through this loop or decreasing the magnetic field through this loop by moving the bar magnet toward or away from the loop. Okay. Now, if we flip the bar magnet, that induces current in the opposite direction. So now I flip my magnet, south is facing up, and I move that magnet toward the coil, and I induce a current in the opposite direction from the situation where I was doing the same thing before the north pole of the magnet. I pull that magnet back out, I induce a current in the opposite direction. If the magnetic field isn't changing through this loop by moving my bar magnet toward or away from the loop, then I don't induce a current. Okay, so this is what we call Faraday's law, and also a little bit of Lenz's law here too in action. So Faraday's law of magnetic induction says that an EMF, an electromotive force, can be induced if there is a changing magnetic flux. What is magnetic flux? So here we have an area in gold, and this and there's a magnetic field permeating this area. Here's our magnetic field vector, and the magnetic flux, represented by this capital Greek letter phi, is equal to the magnetic field, magnitude of the magnetic field, times the area through which we're evaluating the flux, times cosine theta. Theta is the angle between my magnetic field vector and a vector that would be perpendicular to our surface. So Faraday's law, this EMF, this electromotive force induced, is equal to minus the number of turns in a coil of wire, let's say, times the change in magnetic flux over time. Now, magnetic flux, so we just explained here, is related to the magnetic field and the area over which it exists. The unit of magnetic flux is 1 Weber, or sometimes that's also written as Tesla meter squared. Okay, so Lenz's law next. The minus sign here in Faraday's law is a result of something called Lenz's law. This indicates that the induced EMF creates a current and magnetic field that opposes the change in phi, opposite in direction, opposite of sign of the change in phi. Now, the important thing is that this induced magnetic field that we induce by the changing flux is always directed opposite of an increasing magnetic field and in the same direction as the decreasing magnetic field. Okay, so that's what this figure explains right here. Here I have a coil of wire, and I've got my bar magnet moving toward that coil of wire. Okay, the magnetic field from the bar magnet always leaves from the North Pole, so the magnetic field from the bar magnet is pointing to the right in this case. And as I bring that bar magnet toward my coil, I'm increasing the magnetic flux. So the magnetic field that I induce in the coil will want to oppose that increase in magnetic flux, and it will oppose the direction of the magnetic field that's coming toward it. So the induced magnetic field in the coil in this first situation is going to be toward the bar magnet, so opposite the direction of the magnetic field coming out of the north end of this bar magnet. And then that induces a current here following our second right-hand rule. And so the thumb is in the direction of the current, fingers curl around in the direction of the magnetic field. So inside this coil of wire, this solenoid, the magnetic field is going to be pointing to the left. So I put my fingers going through the magnetic coil will be pointing to the left, And so then that means that my thumb points in the direction of current, which would be kind of along these loops right here. Okay, and so then likewise, we can talk about the same situation for all of these 4 possibilities. The 4th possibility is discussed down here in these words, if you want to read through that. So for our scenario B, we had that bar magnet and we're moving it away from the coil. Okay, that is a decrease in magnetic flux, decreasing magnetic field. So when we have a decreasing magnetic field, the induced field will want to point in the same direction. So the field I induce inside the coil is going to be in the same direction as the magnetic field coming from the end of my bar magnet here. Okay, and then we flip the pole, and then but the same scenario still occurs. Okay. So here's an example of a problem to help us practice with Faraday's law. So we have a loop in a figure here that has an induced current of 100 milliamperes. The loop has a resistance of 0.83 ohms. What is the rate of change of the magnetic field in Tesla per second that created this induced current? We couldn't have this induced current if the magnetic field wasn't changing. So what is that rate of change of the magnetic field? And that's what we're going to find here.
In this problem, we're going to think about the induced EMF. Now, the induced EMF, I realize, is a hard thing to understand. So we're going to do a fair amount of practice problems here to think about induced EMF and induced current and induced field. Right. So here we have a loop of wire. My loop only has 1 turn, so it's only looped around on itself once. Okay, and it's sitting in a magnetic field. That magnetic field is into the page. That's what these X's mean. The magnetic field is into the page. So my loop also has a resistance of 0.83 ohms. What is the rate of change of my magnetic field in order to create an induced current? This is my induced current of 100 milliamperes. So my induced current is going to go clockwise around this loop, and it has a magnitude of 100 milliamperes. And with that information, we need to figure out what is the rate of change of the magnetic field. That's the change of the magnetic field over time in order to create this induced field. So if we have a changing magnetic field, we're going to induce an EMF, and this EMF is going to induce a current. That's the 100 milliampere current here. So we have to apply a couple of different ideas in order to figure out what is this rate of change here. Now, my induced EMF is equal to minus N times the change in magnetic flux over the change in time. We've only got 1 turn of our loop, so N here is 1. Okay, so this is minus my magnetic flux. This is the change of my magnetic flux. The magnetic flux is BA cosine theta, and this angle theta here is the angle between B and perpendicular to the area of our loop. Okay, and then we divide that by the change in time. Now in this problem, my area is not changing. So the area can come out of this symbol, the change in symbol. So this is going to be minus area times, we've got the change in magnetic field all over the change in time. Actually, I'm going to rewrite it like this, minus A times delta B over delta T. So that the A is just out here. So our angle theta here, that's our angle between the magnetic field and the perpendicular to our loop. So if this is our loop, I could just kind of skewer it right down the middle, and my pin here is perpendicular to this loop. Magnetic field is also into the page, And so there is no angle between the perpendicular to the loop and the magnetic field. So this would be cosine theta. Theta would be 0. Cosine of 0 is 1. Okay? So cosine of theta is 1 in this case. My induced EMF is going to equal minus the area of my loop, which doesn't change, times the change in magnetic field over the change in time. Okay, that's our induced EMF. But also, we know that from Ohm's law, V, or my induced EMF, is equal to IR. So my induced EMF is going to equal to my induced current times the resistance of my circuit. So I can put these two equal to each other. My induced current times the resistance has to equal minus A times the change in magnetic field over the change in time. Okay, and now I can solve this equation for the change in the magnetic field. So I could divide both sides by negative A. So the change in my magnetic field over the change in time equals minus my induced current times the resistance all over the area of my loop. So I'll go ahead and put in these numbers. Minus my induced current was 100 milliamperes, or 100 times 10 to the minus 3 amperes. I multiply it by the resistance, 0.83 ohms. And then I divide it by the area of my loop, which is just the length times the width. So 0.1 meters times 0.2 meters. So my rate of change of the magnetic field is going to equal all of this stuff right here. It's going to equal minus 4.15 Tesla per second. Okay, the unit has to be Teslas per second because we're dividing a magnetic field divided by a time. The minus sign here means that our magnetic field is decreasing. So this implies that B is decreasing over time. Why? Well, delta B is the same thing as B final minus B initial. So if it's negative, that means that B initial has to be bigger than B final. So that means that our magnetic field is decreasing over time. Okay, so we've got our rate of change of the magnetic field. It's negative because our magnetic field is decreasing over time. If this magnetic field here decreases over time, that's going to induce a magnetic field with respect to this wire here. So this wire is going to want to try to induce a magnetic field to oppose this change. Nature abhors a change in flux. Nature does not want this magnetic field to decrease over time. So the current in the loop will spring up, will be induced in the direction that would create a magnetic field that would attempt to oppose this change. So if it doesn't want the magnetic field to decrease, it's going to try to induce a magnetic field in the same direction as this decreasing magnetic field because it wants to keep that magnetic field the same. So if B is directed into the page, that means our induced magnetic field right here inside the loop is going to also be into the page. So this is my induced magnetic field. So if my induced magnetic field is into the page, if I think about my second right-hand rule, my fingers curl around in the direction of the magnetic field. If my magnetic field is going to be induced into the page above the wire, okay, it's going to be out underneath the wire here, and then my thumb is pointing off in this direction, so that gives me a current that runs clockwise within this circuit. Okay, so that's how you can figure out what the direction of the induced current should be by thinking about, is the magnetic field or is the magnetic flux increasing or decreasing?
And then we're going to practice with Faraday's law and Lenz's law. So here we have a circuit supplied with some EMF from a battery, and we have a resistor in our circuit, and this circuit lives inside a magnetic field. That magnetic field is going to increase from 0 Tesla to 0.2 Teslas in 3.5 milliseconds. And that's going to induce a current in our loop. So what is that current in our that runs through this resistor, which is the current that's going through our whole circuit? And if our current is counterclockwise, we're going to report a positive value. If our current is clockwise, we're going to report a negative value.
Here is another induced EMF, induced current problem. We have a circuit. It's being supplied with a 1.5 volts of EMF from a battery. And there's a resistor here. The total resistance of my circuit, which I need to write down here, the total resistance of my circuit is 10 ohms. And then inside this loop here, we have a magnetic field that is directed out of the page. Okay, so these dots here mean that the magnetic field is directed out of the page. So I'm looking at it here, it's out of the page toward me, or you looking at it, it's out of the page toward you. Okay, so our magnetic field inside our circuit here is going to increase from 0 Tesla, that's our initial magnetic field strength, to 0.2 Tesla, that's our final magnetic field strength. It's going to do this over the course of 3.5 milliseconds. What is the current in the loop during this time when our magnetic field is changing? So what is the strategy to solve this problem? There are actually two currents that are acting in this circuit. Okay, so there's two currents in this circuit. The first current, one of those currents, is coming from the battery. Well, it's coming from the EMF supplied by the battery. The other current is the induced current caused by the changing magnetic field. So that's the induced current caused by the induced EMF from the changing magnetic field. And then so the other current is from changing magnetic field. All right, so the strategy is to figure out what is the total current acting in the circuit. We have to figure out, okay, what's the current in the circuit that's being supplied by the battery? And then what's the current that is induced in the circuit because of this changing magnetic field? All right, so the first one here, so maybe I'll call this 1 and I'll call this 2. So my first current, which is the current that we get because there's a supplied battery here, that current we can get just by using Ohm's law. Remember, V is equal to IR. So the current that's being supplied by the battery, I'm going to call that I battery, is going to equal V from the battery, potential from the battery, voltage from the battery, however you want to call it, divided by the resistance. So the current supplied by our battery to the circuit is going to be 1.5 volts, that's my potential source there, divided by the total resistance of my circuit, which is 10 ohms. So the current supplied by my battery is 0.15 amperes. Let's think about its direction. So we remember that the direction of the conventional current, this is my positive terminal, this is my negative terminal. The direction of the conventional current is away from the positive terminal and toward the negative terminal. So this is the direction of my conventional current from the battery. So that is a current that is clockwise. And I, over here, I wrote these wrong. Okay, we're going to call a clockwise current negative and a counterclockwise current positive. Sorry, I had that written wrong to begin with. The clockwise current is going to be negative and our counterclockwise current is going to be positive. So this is a counterclockwise current. Now, for our induced current, we have to apply to our induced EMF. So our induced current induced, will equal our induced EMF divided by the resistance of our circuit. So we have to figure out what is this induced EMF. Okay, so that induced EMF is going to equal, we'll just think about the magnitude of this induced EMF, minus N, the number of turns of our loop, times the change in flux over the change in time. So there's only one turn of our loop here. We're not coiling around itself. And we're only going to think about the magnitude of this induced EMF. So N is 1. Then we've got our changing flux over time. So the flux would be, so the change in our flux, the flux is magnetic field times the area of my loop times cosine theta. This angle theta is the angle between the perpendicular to my loop here and my magnetic field. And those both align with each other. And so this angle theta is 0, cosine of 0 is 1. And we have to divide this by delta t. Okay, so the thing that's changing here is not the area, it's the magnetic field. So this is going to be A delta B over delta t. So our change in magnetic field is always your final magnetic field minus your initial magnetic field, all divided by delta t. Okay, so now we can find the magnitude of our induced EMF. So that's going to be the area of my loop, which is its length times width. So 0.06 meters times 0.08 meters. And then multiplied by my final magnetic field strength was 0.2 Tesla. My initial magnetic field strength was 0 Tesla. And we divide that by the time over which this happens, which is 3.5 milliseconds. That's 3.5 times 10 to the minus 3 seconds. So my induced EMF, after all of this, induced EMF is equal to, I carry out this calculation, it's 0.274 volts. So that's my induced EMF, and I'm going to put in here to get my induced current. All right, so that's induced current will be our 0.274 volts divided by the resistance of 10 ohms. So my induced current is much smaller than my regular current supplied by the battery. This induced current is 0.0274 amperes. Okay, so we have to figure out, is this induced current clockwise or counterclockwise? Okay, so this is where we apply to Lenz's law here. Okay, what is the direction of my induced current? So the magnetic field inside my loop is out of the page and it is increasing. Nature abhors a change in flux. So the current that gets induced in this loop, that current is going to be induced, it's going to have an induced magnetic field that wants to oppose this increase of the magnetic field inside the loop here. So if the magnetic field starts from 0, but it grows, and this magnetic field is pointing out of the page, the induced magnetic field from the current is going to want to try to keep that magnetic field from growing. Okay, it's going to want to try to oppose it growing, and it's going to want to oppose it increasing. Okay, so the magnetic field that gets induced is going to be directed in to the page on this side of the loop. Okay, B in. Okay, it's going to want to try to induce this magnetic field to cancel out this increase in magnetic field inside the loop. Okay, so here my induced magnetic field is into the page. If I want to think about my fingers curling around this wire in the direction of the magnetic field, that means that the current has to be running in this direction. So my induced current is also going clockwise. my induced current is also clockwise. All right, so if both my induced current and the current supplied by my battery are clockwise, then the total current, I total, is going to be the sum of the current from my battery and the current induced whenever that magnetic field increases, okay, plus my induced current. So that's going to be 0.15 amperes plus 0.0274 amperes. So my total current in the circuit as my magnetic field is increasing is 0.1774 amperes, and it is clockwise, okay? And the convention is to report clockwise currents when we're thinking about kind of the induced currents. The convention is to write clockwise current as negative and counterclockwise current as positive. So if I were inputting this answer into Canvas, I'd want to put a minus sign in front of it, make it negative here, because we've got a counterclockwise current running in the circuit. So in order to solve this problem, we had to recognize that there were two different currents acting in this system. We had the current from the battery and the induced current. So from the battery, we could use Ohm's law to figure out the current supplied by the battery. From the induced current, we had to think about the induced EMF in order to get the induced current. And then we had to think about the direction of those currents and think about the direction of the induced current because of the change of this magnetic field. We add them together, and then we can find the total current in our circuit.